Hi viewers. Welcome to this presentation on power exchange in grid. Grid mode operation of power systems is preferred because of rigid and steady operation due to increased inertia and power number. Frequency is common in synchronous grid. Mismatch of load and generation in constituents systems reflects as inter-system power flow. Multi-system grid can have more than two synchronized power systems. More power systems in the grid have multiple interconnections amongst the systems. Most of the constituent systems may have single or multiple direct links, whereas some systems may not have direct link between but are linked via other systems and operating in synchronism. Consider 5 systems A, B, C, D and E as in the figure. System A and B, System B and C, System B and E, System C and E, System A and D have direct links. System D and E has double link. Whereas System A and C, System A and E, System B and D have no direct link. But all are interconnected and operates in synchronism. Operation and analysis is complex while numbers of power systems in the grid. Variations in load and generation in any system reflects in whole grid. Frequency and inter-system power exchanges changes. In case of two systems, power exchange is between the systems only. Therefore, schedule and actual power exchange is same, having export of one is import of other and vice versa, but is different in multi-system grid. There may be multiple links amongst power systems in the grid. These links may be either direct between the systems or through intermediate system, but all operates in synchronism. Therefore, global accounting procedure is followed to get schedule exchange and actual exchange. Accordingly, each system monitor and control as per its schedule and actual power exchange with respect to the rest of the grid. So each system derives its schedule and actual power exchange with respect to rest of the grid. Schedule power exchange is equal to PSC psi. PSC is equal to entitled power from pooled stations anywhere in the rest of grid. Psi is equal to entitled power for the rest of the grid from pooled stations in own system. Is also equal to total injection of pooled station in the system minus self-entitlement. Actual power exchange is equal to pi pi. Pi is equal to power export on direct links to rest of the grid. Pi is equal to power import on direct links from rest of the grid. For System A, rest of the grid is System B, System C, System D and System E. Direct links are System A to System B and System A to System D. Similarly for System C, rest of the grid is System A, System B, System D and System E. Direct links are System B to System C and System E to System C. Basic case of two-system grid is reviewed for primary analysis. Here is the case of 3 synchronized power systems as simplest form of multi-system. This can have 2 types of setup. First setup has direct links with each systems. Second setup has direct link A and B and C, but A and C have indirect link. Second setup is better to understand the concept. Here is 3 system grid network type 2. System A having generation 6000 megawatts, load 6000 megawatts and bias 240 megawatts per hertz. System A having generation 9000 megawatts, load 9000 megawatts and bias 360 megawatts per hertz. System A having generation 5000 megawatts, load 5000 megawatts and bias 200 megawatts per hertz. System bias consider as 4% of demand in concerned system. Generation and or load is varied in system A, B, and C in different cases. Changes observed for frequency, power exchange between A and B and between C and B. Result compared with area control error. Case 1. 100 megawatts load increased in system A. Frequency dropped to 49.876 Hz. 69.652 megawatts power flow from system B to A. 24.876 megawatts power flow from system C to B. Area control errors. Frequency has dropped, so delta F is positive. System A. Power import, so is negative. System B. Power export to A is positive and power import from C is negative. Net is difference of 2. Net is export, so is positive. System C. Power export, so is positive. Case 2. (200 megawatts generation increased in system B. Frequency raised to 50.250 Hz. 60 megawatts power flow from system B to A. 50 megawatts power flow from system B to C. Area control errors. Frequency increased, so delta F is negative. System A. Power import is negative. System B. Power export to A is positive and export to C is also positive. Net power is sum of two positives. System C. Power import is negative. Case 3. (150 megawatts load increased in system B. And 150 megawatts generation increased in system A. Frequency remains normal 50.00 Hz. 150 megawatts power flow from A to B. No power flow between B and C. Area control errors. Frequency has no change. System A. Power export is positive. System B. Power import is negative. System C. No power exchange. Case 4. 200 megawatts generation loss in System A, and 200 megawatts generation pickup in System C. Frequency remain normal 50.00 Hz. 200 megawatts power flow from System C to System B, and 200 megawatts power flow from System B to System A. Area control errors. No change in frequency. System A. 200 megawatts import is negative. System B. 200 megawatts import from System C and 200 megawatts export to System A. So net is nil. System C. 200 megawatts export is positive. Case 5. 300 megawatts load increased in System A. $150 megawatts generation loss in System B. Frequency dropped to 49.446 Hz. 160.345 megawatts flow from System B to System A. 110.837 megawatts flow from System C to System B. Area control errors. Frequency dropped. So delta F is positive. System A 160.345 megawatt import is negative. System B 110.837 megawatts import from System C and 160.345 megawatts export to System A. So net export is positive. System C 110.837 megawatts export is positive. Case 6. 250 megawatts load added to System B. Frequency dropped to 49.691 Hz. 74.074 megawatts flow from System A to System B and 61.728 megawatts flow from System C to System B. Area control errors. Frequency drop is positive. System A 74.074 megawatts export is positive. System B 74.074 megawatts import is negative and 61.728 megawatts import is also negative. Total import is sum of two is negative. System C 61.728 megawatts export is positive. Case 7. $250 megawatts load increased in System B. Frequency dropped to 49.691 Hz. Power flow from System A and C to System B. Now 100 megawatts generation raised in System C. Frequency improved to 49.815 Hz. Power exchange is changed. Now 200 megawatts generation loss in system A. Frequency dropped to 49.568 Hz. Power exchange is modified. Now 100 megawatts generation pickup in system B. Frequency improved to 49.691 Hz. Power exchange again changed. Now 300 megawatts load shed in system A. Frequency further improved to 50.063 Hz. Power exchange again changed. Now 250 megawatts load added in system C. Frequency changed to 49.752 Hz. Power flow is 156.436 megawatts from system A to B and 98.020 megawatts from system B to C. After all these changes, final status. Generation and load in system A is 5800 megawatts and 5700 megawatts, 100 megawatts surplus. Generation and load in system B is 9100 megawatts and 9250 megawatts, 150 megawatts shortage. Generation and load in system C is 5100 megawatts and 5250 megawatts, 150 megawatts shortage. Frequency 49.752 Hz. Power flow is 156.436 megawatts from system A to B and 98.020 megawatts from system B to C. Now area control errors. Frequency lower than normal. So delta F is positive. System A. Export is positive. System B. Import is more than export. So net import is negative. System C. Import is negative. This is how the frequency and power transfer amongst systems changes with load generation variations in any power system off grid. Request. Please subscribe and share with others. Viewers' comments welcome. Thank you, viewers. Bye until we meet again in next episode.